Okay, hey, it's me, Mr. F, and I got interrupted during the last video, so I just cut it off, and we're gonna start part 3 right now. If you watched part 2, then you know that I was saying that this here function is quadratic, which means its graph is a parabola, and I wasn't sure whether it crossed the x-axis twice just at values that were irrational, or whether it didn't cross the axis at all because its roots were non-real. So I said we would check the discriminant to figure that out. So b squared would be negative 6 squared, which is giving me 36. Take away 4 times the a value, which is 1. Take away the other thing, which is a 1. So that's a positive 32. So it's definitely this situation where I do have two x-intercepts. They just happen to be irrational. So let's go find them. Let me get rid of all this junk. And we'll just start fresh. Nice. Okay. So to sketch this thing's graph, since I can't factor, let's just sketch the graph by finding those x-intercepts, like I said. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. So negative b is the opposite of b, which is positive 6. Plus or minus. Now we just did the math. We just did the math on this and we found it was 32, right? Because it's 36, take away 4. So 32 all over 2 times a, which is 1. So that means my two solutions will be, let's see, 6 divided by 3 is 2, plus or minus 32 is 16 times 2, which if you simplify that is 4 root 2, but divided by 2 is 2 root 2. I hope you followed all that. Anyway, these two guys should be where the intercepts are. So what is 2 plus root 2 root 2? And what is 2 minus 2 root 2? And the answer is, I'm not sure. So let me do that math. All right, I have done the math. And that math is telling me that this particular function has a graph that passes through negative 0.828 roughly. That's 2 minus 2 root 2. And it also passes through 4.828. That's 2 plus 2 root 2. So that would be over here-ish. And again, the positive leading coefficient tells me that this guy opens up. So I don't need to be a heck of a lot more precise here. Just a quick sketch is good enough for me. Because looking at this thing now, I can see that my domain is all reals. And my range is going to be from whatever the y value of this vertex is up to infinity. My increasing and decreasing intervals are going to be, what, negative infinity up to this vertex's x-coordinate. And then from the x-coordinate to infinity. My 11 reb are easy enough. I'll do those right now. The left end behavior. I haven't said this yet, but if you were in algebra 2, you'd probably just say, as x goes to negative infinity, the function f of x goes to positive infinity. I don't want to use that notation. I definitely want to get away from it, and I want to start using the limit notation for sure. So we'll say the limit as x approaches positive infinity of the function f of x equals infinity. So these two notations kind of mean the same thing, but again, this notation that I use for the left end behavior is kind of algebra 2 style, and the calculus style for end behavior is for sure to be treating it as a limit. So do that for me, please. Are we continuous? Yes. Since we're continuous, do we have any discontinuities? No. Do we have any asymptotes? No. Do we have any extrema? Yes. We're going to have an absolute min at y equals whatever this y value is. So, do you know how to find that vertex? I hope you do. There's a couple of tricks to it. We should know, maybe we know, a lot of people don't know, that the x-coordinate of the vertex is always given by negative b over 2a. And then to find the y-coordinate, you would just plug that into the function. If this was f of x, then Of course, you find the y value by just doing f of whatever you just got, negative b over 2a. So that tells me that my vertex occurs at the x value, negative 6 over 2 times 1. So the negatives cancel. 6 divided by 2 is 3. That feels really wrong to me, though, like I've screwed something up. Yeah, I'm just a dum-dum. All right, going way back, like 100 years. Remember when I said 6 divided by 2 was 2? That was funny, right? This is 3, of course. So our intercepts are actually at, of course, 3 plus 2 root 2, and 3 minus 2 root 2, which means this guy goes up 1 to 5. This guy goes down by 1, so negative 1 point. Is that right? No, because it's 3 minus now. So now I'm not so sure about this other guy. Honestly, I don't care though, because I just want to finish this off. But for sure, this vertex is happening at 3. And if you plug in 3, then you get what? 9, take away 18 plus 1, so negative 9 plus 1, so negative 8. So that allows me to go back and answer some questions. That negative 8 is our absolute min at y equals negative 8. And we can do our range now. We know that we go from negative 8 to infinity. We know that our increasing interval is from 3. We said 3. So 3 to infinity, and then negative infinity to 3. So based on the fact that we can find the vertex, we can answer those questions about increasing, decreasing intervals, and extrema. And that's good. All right, moving on. D as in dog. Okay, so I had some people ask about this in class, but the idea for this guy for sure is that this is a rational function. The parent function for rational functions is just 1 over x, which I would love it if you remembered that has a vertical asymptote at 0, a horizontal asymptote at 0, and then it's shaped like a hyperbola. It goes like this. So we know that as long as my rational function is pretty simple, like a linear over a linear, it should have roughly that same shape. So the denominator gives us our vertical asymptote. The 0 of the denominator is 1. So I know that if I go to 1, there'll be a vertical asymptote there. Then I also know that because I have a linear over a linear, and because the degrees are the same, then I take my coefficients. And my horizontal asymptote will be at 1 over 1, which is 1. So there's another asymptote at 1. Now I just have to figure out where my branches land. Are my branches above and then above again? Or is it above and then below? Or is it below and then above? Or is it below and then below again? And you just kind of test it. And honestly, because we're a linear over a linear, you'll never be above and then above again. That only happens when you have higher order component parts to your rational. So really, I just need to test one value, and I'm going to test 0. And plugging in 0, I get, well, 0 plus 4, which is 4, and 0 minus 1, which is negative 1, so negative 4. So at 0, we're way down here at negative 4, which certainly implies that I must be under this asymptote, cruising down through. Then over here, I would be up above, like so. So there you go. And that sketch is decent. It's not great, but it's fine for now. So what's my domain? My domain would be RL numbers except for that vertical asymptote, which is at 1. My range would be RL numbers except for the horizontal asymptote, which happens to also be at 1. My increasing interval is that I don't have one at all. This graph just decreases on 2 intervals. It decreases from negative infinity to the vertical asymptote at 1, and then it also decreases from the vertical asymptote to infinity. So you got to give it as 2 separate intervals. For your left and right end behavior, this will be a little bit different from what we've seen, because this time the limit as x approaches negative infinity of this function is actually a finite value. As I follow this thing left, it approaches the value of the asymptote, which is 1. So it doesn't go to infinity or negative infinity. It approaches a finite value. It approaches the value of the asymptote, which is 1. So when we go to the right, the same exact thing happens. As we go to the right, the function also approaches 1. Is it continuous? We can finally say, no, it's not. And so what kind of discontinuity does it have? It has an infinite discontinuity at x equals 1, which, by the way, means that we have a vertical asymptote at x equals 1. We also have a horizontal asymptote at y equals 1. We don't have a slant asymptote. Do we have any extrema? We don't. Do we have an x-intercept? We do. The x-intercept occurs at the 0 of the numerator, which is -4. So we know -4 is 0 is an x-intercept. We know we don't have any other x-intercepts. Our y-intercept, well, that's the one we used to figure out where we were. We plugged in 0 and got -4. So 0, -4. And that's it. That's the shape of this graph and a whole mess of function properties about it. So let's keep going. E is the natural log of x. So not much to say about this guy. You should know that the ln of 0 is undefined because we have a vertical asymptote there. We know that the ln of any negative is also undefined because there's just big empty space over here. And then the ln of e is 1. The ln of 1 is 0. So here's 1, we get 0. If I went out to e, which is like 2.7-ish, that's when I would get 1. And those 2 points alone maybe sort of help you see the trend. We're going to increase up this asymptote, have an x-intercept here, but then really sharply kind of turn and start to grow really, really slowly. But that's the shape of the ln of x. In fact, that's the shape of any log whose base is greater than 1. Oops, what am I doing? If the base is greater than 1, you're going to see this shape. If the base were less than 1, this whole shape would reflect and would come down and have the look of a graph that was reflected over the x-axis. Anyway, looking at this, what's my domain? My domain is 0 to infinity, but not including 0, so soft bracket. My range is all real numbers. My increasing interval is the entire interval from 0 to infinity. My entire domain is increasing. That means decreasing intervals, none. Now for left-end behavior, we don't exist on the left. So left-end behavior is never the behavior as you approach 0, even if that's sort of the end of the graph. Left-end behavior, by definition, is as you go to negative infinity. You have to go all the way left. And since we don't, then that end behavior just does not exist. Now our right-end behavior, on the other hand, would be the limit as x goes to infinity of this function f of x is equal to, now this graph, it really looks like it's asymptotic, like it's sort of leveling off, but it never levels off. It is growing, it just grows really slowly. So eventually we will actually rise all the way to infinity. We just do it really slowly. Are we continuous? Well, yes, we are, because remember, continuous doesn't mean that your domain is negative infinity to infinity. You don't have to sort of cover all of the possible x values to be continuous. Continuous just means once the graph starts, it can't stop and start again. There can't be a break, right? The graph can never stop and then start again. And this one doesn't. It starts at 0 and then it never stops. It goes forever. So are there any discontinuities? No. And again, that's because the vertical asymptote is not an infinite discontinuity because there's nothing on the other side. It doesn't represent a break in the graph, so it's not a discontinuity. Now, do I have asymptotes? We would say horizontal asymptote, none. We would say vertical asymptote, yeah, there is one of those. It's at x equals 0. And slant asymptote, none. All right, what about extrema? We don't have any of those. What about x-intercepts? We do have one of those. It's 1, 0. What about y-intercepts? We don't have any of those. And that's it. That's the log function. Okay, moving on. Oh, e to the x. Well, e to the x is the exact same graph as the ln of x, except everything got flipped over the line y equals x. So remember when ln of x had a vertical asymptote at 0? E to the x has a horizontal asymptote at 0. Remember how ln of x grew up the y-axis and then kind of leveled off? Well, e to the x is going to very slowly come along the x-axis and then really quickly take off, like that. But there's the sketch. And again, this is true of any exponential where the base is greater than 1. You would have this shape. As long as the base were greater than 1, it's going to kind of stay asymptotic, growing really, really slowly. But then once you get into positive values, it takes off and grows really fast. So what does that make our domain? It makes it our real numbers. What's our range, though? 0 to infinity. You may notice that's the domain and range from a log just switched, because logs and exponentials are inverses, so it makes sense that the domain and range would switch. My increasing interval is over the entire domain, so from negative infinity to infinity. I never decrease, so none. My left-hand behavior exists, and the limit as x goes to negative infinity of this function. Notice it's another asymptote. As I go left, I just approach the finite number 0. But now notice that as we let x go to positive infinity, our end behavior is that we shoot up to positive infinity. So we've got finite end behavior on the left, but an infinite end behavior on the right. Are we continuous? Yes. So are there any discontinuities? No. Are there any asymptotes? Yes. We do have a horizontal one, and its equation is y equals 0. Do we have a vertical one, though? No. Do we have a slant asymptote, though? No. Do we have any extrema? No. Do we have an x-intercept? No, because that's our asymptote. Do we have a y-intercept? Yes, because if x was 0, we would get 1. So it's 0, 1. So there you go. There's another function down. Let's do the next one. 1 over x. So I kind of already talked about that guy. This guy should be a piece of cake because this guy is literally one of our parent functions. We know that it's just down here in quadrant 3, looking all hyperbolic, then up here in quadrant 1, looking all hyperbolic, and then it's got asymptotes at 0 and 0. So I'm going to go fast through this because we already did an example very much like this, but our domain would be our real numbers, except for the bad one, which is 0, the one where we have our asymptote. The range is exactly the same. It's our real numbers except for 0 because of our horizontal asymptote. Then these branches do not increase, but they decrease, and they decrease from negative infinity to 0 on the x-axis, and also from 0 to infinity. My left-hand behavior exists, and it would be the limit as x goes to negative infinity of this function. And that limit, well, we're approaching an asymptote again, so that limit is 0. Then the right-hand behavior is the limit as x goes to positive infinity. And that limit is also 0. Are we continuous? We're not. Do we have discontinuities? Yes. We have an infinite discontinuity at x equals 0. We do have asymptotes. The horizontal one is y equals 0. The vertical one is x equals 0. And the slant asymptote is none. All right. We don't have extrema. We don't have an x-intercept. We don't have a y-intercept either. So that's it for that. H. All right, H is a good one. This is another rational function, and you might be thinking that it could get fairly complicated because the numerator is quadratic, but we kind of talked about this example before, because if you factor the numerator, you get x plus 2 and x minus 2. And then you do have a common factor that cancels out. So I know that this equation is the same as x minus 2, but with a further domain restriction that says x cannot be negative 2. So what that means is the graph of this function, the graph of this top function, as complicated as he looks, he's going to have the same graph as just this linear function. I literally just go down 2, 1, 2, plot a point. And then I make a line that rises 1, runs 1, and rises 1, runs 1. So here's my line. It goes like this. Okay, but wait, there's more. We did say that x cannot be negative 2. So over here at negative 2, we need to poke a hole. And so this equation is actually has a graph that is a line that has a hole in it, and you'd have to address that. So where does this hole occur? It certainly occurs when the x-coordinate is negative 2, and you can just plug in negative 2. Don't try to plug negative 2 up in here, or else you'll get 0 over 0, which doesn't equal anything. Plug it in down here. Negative 2 take away 2 is telling you that that y value is negative 4. So we know where that hole is. Which means we can also answer questions. Our domain is all real numbers. Well, except for that one pesky one, the negative 2. Can't be negative 2. Alright, so our range is all real numbers. But wait, there's a hole in the graph. So we actually never ever get that particular y value of negative 4. So my range would be all real numbers except for negative 4. We can see that this graph is increasing, but again, we do have to split this into two separate intervals. We have to go from negative infinity up to negative 2. Then we start again from negative 2 to infinity. So we give it as two separate intervals. And we never decrease. And the left and right end behavior should be pretty straightforward. We're going to do the limit as x goes to negative infinity of this function. Then we're going to do the limit as x goes to positive infinity of this function. And we can see that as we run to the left, the graph is running down, so that end behavior is negative infinity. Then we can see that as we run to the right on the x-axis, the graph is running up, so the right end behavior is positive infinity. Okay, are we continuous? No. So what's our discontinuity? We have a removable discontinuity, or a hole. And it occurs at x equals negative 2, right? It occurs at the 0 of the denominator, so negative 2 for sure. Okay, so for asymptotes, we don't have any. And for extrema, we don't have any. For x-intercepts, well, we got one of those. Where are we? We're at negative 2. So if we came up 1 over 1 and up 1 over 1, that would just put us on the x-axis at 2. So our x-intercept is 2, 0. And our y-intercept is what we get when we plugged in 0, which was negative 2. Alright, so that's h. I know there's an I. A cube root. Okay, not too bad. So the cube root function is pretty simple. We can literally just plot points for this. So we can go x and cube root of x. And just choose your numbers wisely. 0 has a cube root of 0, which means I can certainly plot a point at the origin. 1 I can take the cube root of, I get 1, so I can plot a point at 1, 1. I can't take the cube root of 2 or 3 or 4 or 5 or 6 or 7, but by the time I get to 8, I know my cube root is 2. So if I go way out to 8, I'll get a point at 2. Then I can do negatives here. So the cube root of negative 1, it's not undefined or imaginary, it's just negative 1. So left 1 down 1 gives me another point. And negative 8 has a cube root of negative 2. So I can go left 8 and down 2. And what you should see is, well, on the right hand side at least, it's a graph that looks a heck of a lot like a square root. But because we're a cube root, we do get this thing mirrored onto the other side. And it looks like we've got odd symmetry where we reflect over the y, then we reflect over the x, and everything corresponds. Okay, so anyway, there's my sketch, which means I can say that my domain is all reals. I can see that my range is all reals. I can see we're increasing over our entire domain, so negative infinity all the way to infinity. We do not decrease. My leb and reb would be the limit as x goes to negative infinity for the function. And we can see that as we go left, the y values are going down, so negative infinity. And for the right-hand behavior, you would say the limit as x goes to positive infinity of our function is positive infinity. Are we continuous? Yes. Do we have discontinuities? No. Do we have any asymptotes? None. Do we have an extrema? None. And then luckily, my x-intercept is the origin, 0, 0, and my y-intercept is the same thing. So we're now done with I, and we can go on to J. Is there a J? And a K? And an L? Feels like I was closer to the end, but I guess not. Okay, so next is absolute value. And probably you remember that all we're doing here, I guess, is we're taking this V and we'll just apply these transformations. The plus 3 is telling me just to take this guy, push it 3 to the left. So off I go. 1, 2, 3. Then the minus 2 is saying go down by 2. So you'd land roughly there. So we'd go 1, 2, 3. We'd go down 2, 1, 2. And we know that that vertex point right there is at negative 3, negative 2. Okay, that's it. That's your graph. So what's our domain? We can see it's all real numbers. We can see that our range has a min at negative 2. So that's going to be negative 2 inclusive up to infinity. We increase along this branch, which starts at negative 3. So negative 3 to infinity is my increasing intervals. But we see that we decrease along this branch, and that's from negative infinity to negative 3. Both left and right end behaviors have us tending towards positive infinity. So you'd say the limit as x goes to negative infinity is that the function is still approaching positive infinity, and the limit as x goes to positive infinity of this function is also just positive infinity. Okay, so now are we continuous? Yes. So what's that mean about discontinuities? It means there are none. What about our asymptotes? None. What about our extrema? We've got an absolute minimum at y equals negative 2. So no other extrema that I can see. So who's our x-intercept? Looking like it's negative 1, 0. Who's our y-intercept? Looking like it's 0, 1. And that's it. That's how I would deal with this absolute value guy. What's k? Just radical, easy enough. So k is the same deal where you should pretty much be able to handle this because you memorized that the parent function was like just half of a parabola knocked on its side. So what's the effect of the minus 4? Well, we just said that. We just said that like adding 3 kicked us 3 to the left. So taking away 4 must kick us 1, 2, 3, 4 to the right. So there's our graph. And from it, we can answer questions about our domain. We can see that only 4 or greater are in our domain. For the range, we can see that only 0 or greater is in our range. We are increasing on the interval from 4 to infinity. Notice that the domain might include 4, but I can't include 4 as part of my increasing or decreasing interval. You just never ever include the endpoints. Always make them open-ended. Decrease, never. Left-hand behavior does not exist, because remember, the left end is not this point. The left end is when I go all the way to infinity, And you can look for the graph all you want, but it ain't there because the graph doesn't start till 4. Alright, my right-hand behavior exists though, and it's that the limit as x goes to infinity of the function is infinity. Okay, are we continuous? Yes. Because again, continuous didn't mean that we cover the whole x-axis with values. It just meant that once you start, you can't start and stop, or stop and start. None. None. I do have an extreme value, and it's a global min, and it's y equals 0. My x-intercept is 4, 0, and my y-intercept is that we don't even have one. So there you go. There's some properties of this particular radical function. Then we get to this guy. And honestly, I don't remember what this guy looks like. I think we need a graphing calculator, truth be told. I don't remember how to graph this. So I'll plot some points. So 0 squared would normally give 0, but the plus 4 is kicking it up to 4. 1 squared would give 1, plus 4 is 5. 2 squared is 4 plus 4, which is 8. 3 squared? Oh, but it's the root of that. It's root 8. And that's root 5. And that's 2. Okay, whatever. What's that telling me? Yeah, I don't remember. Okay, so since I'm not really sure what the graph looks like, let's answer these questions anyway about domain. You should still know, even without a graph to look at, that your domain is all real numbers. Because the very first thing we're doing is squaring x. So it will never be negative. And a not negative thing plus 4 will never be negative. So there is not a single value of x we could come up with that quote-unquote doesn't work in this equation. It's always going to be the square root of something positive, which will always be real. Now, for the range, we're not ever going to get negative. In fact, the smallest thing we would ever get is 2 if we let x be 0. And then everything else is going to be bigger than that. So how's this look? I really want to know how this looks, but I can't picture it. So I'm going to go graph it. Okay, here's the graph, which means I was wrong. But how was I wrong? I said minus. I graphed with a minus. My bad. So you know what? Let me bring Desmos up. We can all look at it together. If I remember how. Just looking like I don't. It's not really working. Because I'm probably looking the wrong one. Alright, let me find this thing. Okay, I got it. And I'm not sure how you can tell if this is showing up well or not, but you can see that I definitely put the minus. Let me put that back to plus. And that's kind of what I expected. It definitely felt like it was giving us this shape that's sort of parabolic in shape. It's not a parabola, but it kind of feels parabolic. So yeah, why don't I fix that? So let me turn this off. Okay, that's out of my way. This wrong graph can go back in the garbage. And then we can keep on answering our questions. So we are getting essentially just roughly a parabolic looking thing that had its minimum value at 2. So the domain was all reals. The range will be 2 to infinity. Increasing interval would be 0 to infinity. Decreasing is negative infinity to 0. The leb and reb are both going to infinity. I'm not going to write it out because I'm getting bored. But are we continuous? Yes. Do we have any discontinuities? No. Do we have any asymptotes? No. Do we have any extrema? Yep. We have an absolute min at y equals 0. X-intercepts, we don't have one. And y-intercept, we have 0, 2. So this is kind of a strange one. There are times when you should know your function properties from just the function rule algebraically, but other times you would want the graph. And so if you don't know how to get to the graph from the function rule, that might be a problem. So ask me about it. We'll try to figure it out. Oh no, I clicked a button and it made things weird. Let me try to fix it. I can't. And if I turn the page? Alright, we now have blue margins. That's okay. Because I don't know how to fix it. So it's got to be okay. Okay, whatever. Alright, I wonder if I should go over number 9. I feel like I probably shouldn't because I know I went over it a bunch of times in class, but these videos are meant to be here forever, for the rest of my life, so let's not skip anything. Okay, so draw a line. Draw another line. Again, the way these piecewise functions work is you want to go ahead and let these intervals define certain intervals. So for all the x's less than 0, that would be, alright, up to 0 and anything to the left. Then in green, from 0 to 3, that would be sort of fill this guy in and go out to 3, but stop at 3 and 3 is open. And then in blue, anything greater than or equal to 3 will fill that guy in and go that way. So by the time we're done, the whole x-axis should be covered in functions. But again, in this red area, I should only see the graph of x squared. And plugging 0 into x squared gives 0. So there's truly a point here. Although that should be open, we said, right? That's open. And then -1 gives 1 and -2 gives 4. So we should see half of a parabola this way, and it should be open at the end. Then in green, plugging in 0, 0 plus 2 gives us 2, so we would get a solid dot up here at 2, and plugging in 3 gives 5, so 1, 2, 3, 4, 5 would be up here, but this end should be open, and to connect the dots we would see the shape of a line. And then lastly, in blue, 4 is just a horizontal line, and remember this guy's up at 5. So 4 would start here, it would be a solid dot, and it would go this way. So those three pieces make our piecewise function, and all the stuff I put down here on the x-axis would go away, because we were just using that as a temporary guide. But when you're done with the piecewise, I should only see the 3 branches I'm supposed to see. So I see my parabola, I see a linear, and I see a constant, and that's it. Finally we get to 10, and this has a lot of parts. How many parts this time? Going all the way to I? Okay, if you say so. And I think I pushed through a lot of these in class too, so let's just go through this fast. This guy is a quadratic, so you need them set equal to 0, so we'll go 2x cubed squared plus 5x minus 3. And if I can factor this, then that's what I'm doing, because I want this thing factored. That's the easiest way. So if I factor, I get a 2x and an x. That's for sure. Then what numbers do I want? Well, you do 2 times -3 to get -6, and you consider those factors. Now 1 and -6 add together to give -5, but we want a positive 5. So why don't we try -1 and positive 6? That would give a positive 5 in the middle, right? So these must be my 2 preferred factors. Now notice I already have a 2. So to get this factor of 6, I only need a 3 here. 2 times 3 will make 6. And to get the -1, I need to put a -1 here. And this guy's going to want to be plus. So this is my fully factored form. How do I know it is? Well, because I can double check it. I can FOIL this. And I would get a 2x squared plus 6x minus 1x minus 3. These middle terms are the ones that need to combine. So you get a 2x squared plus 5x minus 3. That's what we wanted to get. So I know this factored form is correct. And that means I know that my solutions are just the zeros of these terms here. So setting this equal to 0, I just add 1 divided by 2, and I get x equals 1/2. But the other entry in our little solution set is whatever number makes this thing come out to 0. So pretty obviously, I hope, that's -3. And there's your two solutions for 10a. Okay. In part B, we can solve this pretty easily. You just take the square root of both sides. But it's important to remember that whenever you take the square root of both sides, you need to be generating a positive root and a negative root. So the square root of 9 could be +3 or -3, which means by the time you add 5 to it, you're going to get two different answers. You're going to get -3 plus 5, which is 2. Then you're going to get +3 plus 5, which is 8. So here's another equation with two solutions. What about part C? Yeah, so C is an inequality. And the fastest way to approach an inequality is to find its zeros. And so we know this thing equals 0 at -3. And this guy equals 0 at +3. So that means I essentially just need to test this expression. All we care about is it positive? So I just need to test this expression and find out if on each of these intervals I'm positive or negative. And right now it's pretty simple to where I could do it in my head, but a better plan is to build a whole big old table. And what we need is one column for every single interval. So we've got an interval here that goes from -infinity to -3. We've got an interval here that goes from -3 to 3. Then we've got an interval that goes from 3 to infinity. And in the middle of these intervals, we equal 0. And in the middle here, we're 0. So all you really got to do is test these. And one quick way to test them is to just grab each factor. Grab the x plus 3, grab the x minus 3, and then you can easily test the whole product, x plus 3 and x minus 3. So give all of these guys rows. You get a row. You get a row, you get a row, and you get a row. And so it's very easy to tell just the sign. I know that if I'm less than -3, then adding 3 won't make me positive. I'll still be negative. But as soon as I'm bigger than -3, then adding 3 will make me positive, including over here. If I'm taking away 3, then something already negative, take away 3 more, it's definitely negative. If you take away 3 from something that's not even as big as 3 yet, that's going to be negative. But if you're taking 3 away from something bigger than 3, that's going to be positive. Now, I'm multiplying. So this is telling me that on this interval, we would be doing a negative times a negative, and we would get a positive. But in this middle interval, you'd do a negative times a positive, and you'd be negative. And in this last interval, you'd be doing a positive times a positive, which is positive. So there you go. If our solution set is just to figure out when this thing is positive, well then it's here and here. So my solution set is the two intervals on the ends, the ones that go from -infinity to -3, and the one that goes from 3 to infinity. So that's your solution set for part C. What's D looking like? Oh yeah, this guy. Okay, so to solve a log, we said we would use the product rule, which says that these two logs can combine into a single log where you're doing x times x minus 3. So you turn the sum of two logs into a single log where you're multiplying. Then that whole thing equals 1. Now from here we want to convert from logarithmic form to exponential. So this understood base is a 10. So my exponential form would be 10 to the power of 1 equals x times x minus 3. So 10 to the 1 is obvious. That just stays 10. Over here I would distribute the x to get x squared minus 3x. Then that's a quadratic. So I'm subtracting 10 from both sides. Get it into standard form. that I'm factoring. Which tells me that the two zeros are -2 and 5. Okay, so that's a log equation. Then I think we're in for, an absolute value one. Okay, so these can be a little tricky until you remember that absolute value bars, they do two things. If you're already positive, well then they don't do anything. But if you're negative, then they change your sign. So let's assume this thing was positive, x minus 3. Well then the absolute value bars wouldn't have to do anything to it, so I can go ahead and just take the bars away. And I can solve this first case to get part of my solution set. Now the second case is, what if x minus 3 actually came out negative? Then the absolute value bars would have to change its sign, essentially by just multiplying the whole thing by -1. That would turn it back into a positive, but we still want to stay less than 7. So here's my two equations that I have to solve. First one's pretty simple. You add 3 to both sides and you get x is less than 10. This one's a little less simple. You probably want to just distribute the negatives. You get negative x plus 3. Nothing weird yet. We're still less than 7. Then you subtract 3 from both sides. No sweat there either. That just turns us into a 4. Then you multiply or divide by a negative. Remember, that will always make the sign switch. And this 4 turns into a -4. So there you have it. Between those two solution sets, just draw yourself a number line and figure out either where they overlap or what two regions they share together. So it says here we need to be bigger than 10. Okay, so assuming that's 10, we're open here and we go to the right. Then there's -4. So if this is -4, then 0 would be right about there. Who cares? But we would be open, and anywhere less than that? No, this says greater. So x has to, okay. So I'm doing this wrong. If I'm trusting my own algebra, which I kind of am, then it actually says x needs to be less than 10, which means I can't be 10, but I can be somewhere left of it. Then x has to be bigger than -4. Well, here's -4. I can't be -4, but I can be anywhere to the right of it. This seems like one of those problems where you're looking for the overlap. And we can see that the overlap is only the stuff between these two values. So our solution set is going to be that x is an element of the set that starts at -4. And then it ends at 10. And those have to be soft brackets because those are open-ended intervals. But that's right, -4 to 10. And after E comes F. And F is the kind of messed up one. It says solve for x. Alright, so assuming t really is just a variable, then solving for x just means getting x alone. And that just means saying that x equals e to the 2t minus 3. That's literally what x is equal to. So we're kind of just done. There's nothing more to do. That's the equation. That's it. So here's G. To solve G, I still strongly recommend that you subtract the 3x from both sides. Get it set equal to 0. And now to solve, you can factor out a 3x. That leaves you with a 4x minus 1. We are now factored. We have our two factors. So if you let 3x equal 0, that'll give you a solution. And if you let 4x minus 1 equal 0, that'll give you a different solution. Here I'm just dividing by 3, so I get 0. And here I'm adding 1, then I'm dividing. So I get x is 1/4. So the total solution set to this pretty simple seeming equation is that x is an element of the set that contains both a 0 and a 1/4. So that's 10G, and then 10H So just h and I. And we did h and I already, I think. H is pretty straightforward as soon as you recognize that 27 and 9 are both powers of 3. So 27 is really just 3 cubed. And then you're raising that to the power of 2x. Then 9 is really just 3 squared. But then you're raising that to the power of x minus 3. Alright, and when you raise a power to a power, you're multiplying. So this is 3 to the 6x, which is equal 3 to the 2x minus 6. And at this point we can invoke a rule called the one-to-one property that says if these things are equal, then the exponents have to be equal. The bases are already equal. So for the whole expression to equal the whole expression, it would have to be true that the 6x equals 2x minus 6. So we're just kind of like making an intuitive leap here, but it's fair, we're allowed to, and we can solve this. We subtract 2x to get a 4x that equals negative 6, then we divide by 4. Then of course we do not forget to simplify. These are both divisible by 2, so you get negative 3 halves. And that's h, and then lastly we get I, which is a pretty easy one. To solve this, you just want to take the ln of both sides. We have a base of e, so we use a log whose base is e. Then, because I took the ln of this expression, I can pop the 3x out. Just let that get multiplied by the ln of e. The whole thing's supposed to equal the ln of 5. But the ln of e, remember, the ln of e, that's just 1. So 3x times 1 is 3x. And that now equals the ln of 5. Then you just divide by 3 to get done. Cancels. So we end up with x equals, now remember that 3 doesn't go with the 5. The 5 is sort of trapped in parentheses. So this 3 will be like a coefficient of a third on this ln. And that's sort of my best possible answer. The other thing we could do though is use the power rule to pull that 1/3 back in. Then we would get the ln of 5 to the 1/3. But that's the same as the ln of the cube root of 5. So there will somewhat often be lots of different possible versions of the answer. I'm still going to stick with this, just keeping a nice basic expression that I'm taking a third of. Over here, I don't know, I don't love rational exponents, and down here I don't love radicals. But both of these are fine, so however you left your answer would be okay. I think that's everything, finally. You know, it's a good thing because I'm getting tired. But again, I hope these videos are helpful to someone, and they'll be here. You can reference them whenever you need to, but we can talk more in class on Tuesday. Bye.